Hi guys, so today we're going to be talking about equilibrium. Before now you've been playing the equilibrium game, and I'm going to be referring to a few of the things you saw and did during that game in our lesson today. So the first thing that I want you to know about equilibrium is that in chemical systems, when we say equilibrium, we're usually referring to a dynamic equilibrium. And in a dynamic equilibrium, the rate of the forward and the rate of the reverse reactions are equal, making there be a state of balance. You saw this in practice in the game that you played. The concentration of the reactants and the products also become constant. Now, we're going to talk about how those are related and how they are different from one another. So let's talk a little bit about what equal and constant actually mean. So if the rate of the forward and the rate of the reverse reactions are equal, it means that they are each happening at exactly the same speed. Okay? So it means for every one forward reaction, we are also getting one reverse reaction. That is the definition of equal. However, constant is something different. The concentration of the reactants and the products individually become constant, which means we will reach a level where the concentration of the reactant does not change and the concentration of the product does not change, but they do not have to be equal to one another. And that's where people sometimes get confused. We're going to be talking about that quite a bit in our lesson today. So in summary, our forward rate of reaction and our reverse rate of reaction will be equal when we're in a dynamic equilibrium and our concentrations become constant. A great way to remember that is actually the phrase RECC. R-E-C-C. Rates are equal, concentrations are constant. So here's an example. If we have gaseous water reacting with carbon monoxide, we can have an equilibrium reaction where we are also producing hydrogen gas and carbon dioxide. Okay? Now we have forward and reverse arrows, or a double-ended arrow in this case, and the reason why we have this double-ended arrow is because the reaction goes both in the forward direction and in the reverse direction. It is a reversible reaction that can reach equilibrium. So if we were to do that as a graphical representation, we would say A becomes B at the same rate that B becomes A. So if we had a percentage of A decreasing, while the percentage of B would increase until equilibrium is reached. So equilibrium is reached when the rate of the forward reaction is the same as the rate of the reverse reaction. Now I want you to note, equilibrium can only ever be achieved in a system where the products and the reactants cannot leave. This is called a closed system. If anything can leave the system, we can never reach a point where we have a true equilibrium because something's escaping, which means if we have a product that's escaping, well, when we go to reverse, we no longer have that to become a reactant in the reverse reaction. So let's talk about some non-equilibrium reactions. These are reactions that never reach equilibrium, that will always go to what we call completion. So the first rule is if any reactants or products can leave, then we will go to completion. We will not have an equilibrium. If a precipitate is formed, remember, a precipitate is something that becomes insoluble in a liquid and thus becomes unavailable to react. If something is unavailable to react, it's the same as it leaving that system. So we can't reach equilibrium. Our third rule is if a gas is formed in a non-closed system. So let's say we're doing our reaction in a test tube. The test tube has a cork in it. Well, can the gas that's being produced get out? No, it can't. But if we have an open test tube, then that gas can escape, and that would cause our system to not be able to reach equilibrium. So if any of these are true, there will not be equilibrium in our system. So there are actually several types of equilibriums that we might experience in chemistry. Chemical equilibrium is only one of them, and it's the main one that we're going to discuss, but there are some others, and I'd like to touch on those now. So the first is phase equilibrium. We hit a phase equilibrium in the middle of a phase change. If you remember back to our phase change curves, or heating curves and cooling curves, you'll remember that when we're actually changing phase, our system exists in two states of matter. If you are, for example, melting, you start as a solid, you end as a liquid, but during the phase change, you have both. Well, we can have a phase equilibrium in a closed system if we hold that system at exactly the melting or freezing point for that substance. And we will always have an equilibrium between our liquid and our solid component. This is the reason why your freezer on your refrigerator is actually set quite a bit below the actual freezing point of water, because we need it to come out of that equilibrium to actually become fully frozen. So initially, the substance would be all in one phase, and then it would shift over into two phases, and if we went out of the equilibrium, we would end in a completely different phase. So to recognize a phase equilibrium, you have to have the same chemical formula or substance on both sides of your equation, just shown in different phases, with nothing else present. For example, if you had liquid water on one side and gaseous water on the other side of your formula, then that would imply a phase equilibrium change of boiling or vaporizing. So let's look at our example. If we have liquid water and we add energy, we can form gaseous water. If we held this physical change, this phase change, at exactly the boiling point of water and never let it go higher and never let it go lower, we could potentially stay in a phase equilibrium where we always have some of the substance as a liquid and some of the substance as a gas. The difference here is it would have to be a fully closed system. Solution equilibriums are another type of equilibrium. Now, we can get a solution equilibrium when we have a gas dissolved in a liquid. This would be an equilibrium between the undissolved gas above the liquid and the dissolved gas in the liquid. When you buy a bottle of soda, Pepsi, Coke, Mountain Dew, whatever you like, okay, it is at that moment in a gas to liquid solution equilibrium. The moment you crack the top, the moment you take off the lid and you hear that hiss, you've just destroyed the equilibrium that existed in that system because you've allowed the undissolved gas above the liquid to escape. You opened the system. So what type of conditions favor dissolving a gas in a liquid? This is a throwback. What will keep a gas dissolved in a liquid? Well, if you answered cold temperatures and high pressures, you're absolutely correct. Remember, it's the same type of conditions that would keep your soda fizzy. So we want a high pressure and a low temperature. Now, for solids and liquids, dissolving and crystallization occur at the same time. And if you remember back to solutions, when we have an equilibrium system, this would be a system that is saturated. Saturated solutions are in equilibrium. So an example of that would be salt dissolving in water. Remember, a saturated solution is a solution where no more solute can dissolve, and it is constantly dissolving and recrystallizing at exactly the same rate, so you see no net effect. That is how we defined a saturated solution. A saturated solution is one where the maximum amount of substance is dissolved under the current environmental conditions. Our third type of equilibrium is chemical equilibrium, and this is the one we're going to be spending the most time with. In a chemical reaction, when the reaction starts, the only reaction happening is the forward reaction, because all you have is reactants. You saw this in a couple of the video clips we watched, as well as in the game that you played. As the reaction progresses, you build up more product, and this then allows the reverse reaction or the left shift to begin. This goes until the rates of the forward and the reverse reaction are completely equal. When these two reaction rates are equal, we say that chemical equilibrium exists. So let's draw a graph of what this would look like, with the rate of reaction on the y-axis and time on the x. We're going to use a solid line for the forward reaction and a dotted line for the reverse. So here are our two axes. We have rate on our y and time on our x. We're going to use a solid line for the forward reaction and a dotted line for the reverse. Well, at the beginning of the reaction, we have a lot of reactant. And because we have a lot of it, that means according to collision theory, the reaction will happen very quickly. But as that reaction proceeds, we're going to have less and less reactant to react. And so the reaction rate will normalize at a low level. Now, because this is reversible, we are going to start off with no product to turn into reactant. Whoops, sorry, that was supposed to be a dotted line, wasn't it? Let's fix that. Let's make it a dotted line. So our reverse reaction, we start off with very little product to react, but as the reaction proceeds, we continue until we have more and more of that product that can turn back into reactant. And if you look in the area here, this is where our rate of the forward reaction and our rate of the reverse reaction have become equal when those two lines overlapped. Now, catalysts. We know that catalysts affect the rate of a reaction. They make it go faster. But how will that affect an equilibrium? Well, it's interesting. Catalysts have no effect on if a reaction will reach equilibrium or not. If a reaction was going to go to equilibrium, a catalyst won't make it happen if it wasn't going to happen in the first place. What a catalyst will do is, because it speeds up the rate of that reaction, if it will reach its equilibrium faster, but it won't change any of the concentrations. So all it would do would be to make that curve come together sooner. It doesn't make it go to equilibrium if it wasn't going to go there anyway. So it speeds up the reaction, but if the reaction was going to go to equilibrium, it will go there anyway. Just makes it faster. So let's look at example 6. Determine which of the following systems are in equilibrium and which are not. Provide a reason for your answer. Also state if the change is physical or chemical. So you have A, solid copper 2 sulfate is added to a closed flask. It dissolves completely in water, forming a saturated solution. B, a drop of acetone is added to a closed flask. And C, 50 milliliters of water is placed in a closed flask. I want you to consider each of those situations. Tell me if they are in equilibrium or not, and if those changes described are physical or chemical. So A, we're dissolving solid copper sulfate in a closed flask to become saturated. The key there is saturated. That would reach equilibrium. Now it's dissolving, so that would be a physical change. B, a drop of acetone is added to a closed flask. The key here is that it's a single drop. This probably wouldn't go to equilibrium. That drop would evaporate and we wouldn't have that constant back and forth from the liquid to the gaseous state. However, 50 milliliters of water placed in a closed flask, in that case, yes, we might get a gas to liquid equilibrium. All three of these would be considered physical changes. None of these are chemical changes. Let's look at example 7. Which type or types of changes can reach equilibrium? A, a chemical change only, B, a physical change only, C, both a chemical and a physical change, and D, neither a chemical nor a physical change. So the correct answer here would be C. Both chemical and physical changes can reach equilibrium. I hope you didn't get thrown by the fact that in the last problem, all the examples I gave were physical. Here we could have physical or chemical. So that's it for equilibrium right now. In our next lesson, we're going to look at Le Chatelier's principle. Have a great day.